Hello, my name is Georgi Popov. I'm originally from Russia, and now I'm a PhD student in Finland at the Department of Chemistry of the University of Helsinki, and I study Atomic Layer Deposition of Perovskite Solar Cells. To give you a better idea of my work, I will briefly introduce you to the current solar cell landscape. Silicon solar cells are the oldest commercially available solar cells, and they have dominated the photovoltaics market for as long as it exists. Their success can be attributed to their high efficiency and the abundance of silicon. However, silicon also comes with its own set of disadvantages. While silicon is abundant, we cannot just use any source of silicon to make solar cells. Solar cells require high purity silicon made by expensive methods. Limitations imposed by physical properties of silicon create additional challenges. Efficient light absorption requires thick silicon layers, in other words, a lot of high purity silicon, which is why silicon solar cell companies break out in cold sweat every time high purity silicon price fluctuates. To make matters worse, silicon is poorly suitable for applications that require flexibility, transparency, or color tunability. The new generation of solar cell materials, like halide perovskites, tries to address these challenges. Perovskite solar cells are thin film based and only require a few hundred nanometers thin layers. They are compatible with flexibility, can be made semi-transparent or colored, and are prepared from inexpensive and abundant materials. But what are these halide perovskites? Halide perovskites are a group of compounds with a similar structure as the mineral perovskite. However, they consist of completely different chemical elements. For instance, this most studied halide perovskite consists of an amine, lead, and iodine. What makes these perovskite compounds special are their remarkable optoelectronic properties and simple laboratory scale processing. Because of these properties, perovskite solar cells were able to rival silicon solar cell efficiencies in record time. However, perovskites are not without their own challenges. First and foremost, their high efficiency is lost when the perovskite deposition is scaled to large areas because of the losses in quality and uniformity of the perovskite film. Secondly, perovskites are unstable in ambient air, and upon exposure to it, they rapidly degrade with the loss of functionality. Now, I believe that both of these challenges can be addressed with atomic layer deposition. Atomic layer deposition, or ALD, is a method to deposit thin films with an exceptionally high quality. Its working principle makes it inherently scalable to large areas in roll-to-roll manner and to large batches. It is an industrially established technique with a €1 billion worth market. Its commercialization was pioneered in Finland by Dr. Suntola, whose achievements were recognized with the Millennium Technology Prize. And if you are by any chance using a mobile phone or a computer on a daily basis, then know that you are using components made with ALD on a daily basis. But how does ALD work? ALD utilizes reactive surface sites present on most surfaces. In an ALD process, these sites are exposed to a chemical or a precursor which reacts with them. However, such exposure leaves an excess of precursor and reaction byproducts, which is why in ALD a purge with an inert gas is used to remove this unwanted species. Next, the second precursor is introduced, which reacts with the first one, still bound to the surface, followed by another purge to remove unwanted species again. Together, all these steps complete one ALD cycle in which, as you can see, we manage to deposit a little bit of material. Repeating these cycles many times is how films grow during an ALD process. And this is how ALD looks in practice. The major part of my work consists of developing ALD processes which I do on a commercial F120 ALD reactor like this one. But what does ALD process development has to do with the perovskite challenges I mentioned earlier? Well, one of the perovskite issues was their scalability. And as I just said, ALD is inherently scalable. So depositing perovskites with ALD would address the scalability issue, right? Well, unfortunately, when I started my PhD project, there were no known ALD processes capable of depositing simple metal iodides, not to mention more complex halide perovskites, which is why I had to develop a new process for them. But how? Well, at the heart of every ALD process are the precursors, which react with each other to produce the desired material. In my case, I used previous knowledge on ALD of various lead compounds and metal fluorides to devise this precursor pair, lead BTSA and tin tetraiodide. With these precursors, I was able to deposit high-quality films of lead iodide. And with an additional gas treatment step, I was able to convert these lead iodide films into the perovskite films. However, these perovskite films rapidly degraded in ambient air, so I also had to address the stability issue somehow. Now, ALD can be used to encapsulate air-sensitive materials. However, most ALD processes require temperatures which perovskites cannot withstand, which is why I developed two new low-temperature processes compatible with the perovskite to prevent their degradation in ambient air. With these two processes, I could deposit films of lead sulfide on top of the perovskite films, which effectively sealed them from reaction with ambient air. Furthermore, lead sulfide films are not just an extra encapsulation layer. Lead sulfide properties enable it to act as an active component in the solar cell. This opens up opportunities to simplify the solar cell structure and to enable the deposition of the whole cell with ALD. To summarize, I have shown you how I apply my expertise in chemistry and materials science to develop new atomic layer deposition processes. These processes aim to resolve challenges of a new promising generation of solar cell materials, halide perovskites. Perovskites, in turn, strive to fill the gaps left by established solar cell technologies like silicon, and I believe that by filling those gaps, we can achieve abundant, accessible, and inexpensive solar energy. Last but not least, I would like to thank all the people and the agencies who made my work possible.
Thank you, Georgi. Your topic is, I would say, in the when we are developing new solutions for renewable energy, I think it's in the front line of what is being done. Very nice to have you here. If I got it correctly, the biggest challenge is the stability, but it seems that you have cracked this one already quite well. So how would you comment on this? Do you have already a solution for the stability, or is it still an issue?
Well, my solution is kind of one of the many solutions there are to this stability problem. I guess in the end, we just have to make some kind of like a grand comparison to figure out who actually like nailed it. But from the results I've got, yeah, it's looking pretty good in that direction.
So if you think about the application of this technology, what would be your favorite application that you see these perovskite cells first applied in real life?
I think the coolest thing would be to exploit their kind of property that you can make solar cells flexible and transparent or semi-transparent and colored in a way that if you think about solar cell installation, you have to hire somebody and then the person comes with a drill, a lot of like supporting material to install that. But if you have flexible solar cells, you come with a roll, you unzip it, kick it, and connect it to the battery that you are using. But also this kind of physical flexibility, it also gives a lot of so to speak, creative flexibility, because you can put these solar cells on cars, for example, because now you can follow the shape of the object, or you can integrate them into furniture. And I'm now talking about like outside furniture. For example, you have in cafes at summer, you have these big umbrellas, so these can be made of solar cells. I think that would be one of the coolest things.
Great, that sounds really cool.
Yeah, like generating energy everywhere, basically.
Yeah, all surfaces in a way could be.
Yeah.
That's really nice. Okay, thank you very much for being part of this. All the best and good luck with your thesis.
Thank you. Thank you.
Thank you.